This is section 2.2 on functions and mappings, and basically a mapping diagram basically shows you what happens or what a function does to all its input values. So this little oval shape represents all the inputs, the values that goes in, and it shows you where those outputs go. Now the name that we give to the input values, the set of values that go in, we call the domain, and the set of output values, the values that come out, we call the range. Yeah, so the domain represents the set of values that can go in. They may just be positive numbers, they may be all numbers, and the set of outputs we call the range. Now for some functions, every input value goes to a single output value. Okay, so let's look at the different types of functions that we can get. So we can get some functions where first one is each input goes to only one output. So an example of that might be function 3x plus 2. Every value you put in goes to a different output value, and when that happens we call the function one-to-one. So this would be an example of a one-to-one function. Yeah, every input goes to just one output. The second type is where you maybe get each input or some of the inputs, it may not be all of them, each input, let's change that to some rather than each because it's not true for all of them, some inputs may go to the same output, might go to the same output. So you put a number, two different numbers in, and they go to the same output number. So an example of that might be f of x equals x squared. So if you put the number 5 in as x, that maps or goes to 25, but also if you put -5 in, that also goes to 25. So there are lots of values where the inputs may be the same, but the inputs may be different, but they go to the same output. If that's the case, the function is called many-to-one. Many. So this would be a many-to-one function because each input or different inputs can go to the same output. So these are examples of functions. Now the one we haven't done so far is where you may have one input. So you may have one input going to many or more than one output. So that's a number that you put in that could go to two or more different places. So for example, if our function was the square root of x, then an input of, let's say, 9. So if you've got 9, you put 9 in. Well, 9 could go to 3, or it could go to -3. So you've got an input that can go to more than one output. That's not a function. And there's also another problem with square root x and some other functions as well, in that we have some inputs that don't have an output, So for example, if you had an input value of -4 and you try and work out the square root of -4, well, it's got nowhere to go, isn't it? Because we haven't got a definition yet anyway for square root of negative numbers. So we would have inputs like dots on this side of the oval, but no arrow. So these can be functions 1 to 1, and these can be functions many to 1. So strictly speaking, what we're talking about, a function is something where each input must have one distinct output. Yeah, that's what makes a function. So each input must have a unique, let's use the word unique, a unique output, which 1 to 1 and many to 1 functions have. Whereas this last one here, which we actually call 1 to many, so let's write that down, 1 to many doesn't have that. So a 1 to many function, you cannot say each input has a unique output. Each input, well, here it has 2 unique outputs, or it may be that an input doesn't even have an output. So these would not be functions, but what we'll be looking at is how we can restrict the domain. If we restrict the types of numbers that go in, we can make this happen. So we've got different graphs, different diagrams, and for each one, what we need to do is to state what type it is and whether it's a function. So A, for each part, we've got 2 bits. So first of all, that's 1 to many, isn't it? 1 to many. Does each input have one unique output? No. So that it means it's not a function. Right, let's have a look at B. Now you can tell if something is a function by its graph. So our inputs are along here and our outputs are along there. Now if it's got no gaps in it, that means every input's got an output. Yeah, so if anywhere you go along the x-axis, you'll meet the y-axis. And also we can't have an input going to 2 output places. That doesn't happen. Yeah, so this would be 1 to 1. Each input goes to 1 output. So this is 1 to 1. And we know that anything that's 1 to 1, or that is a function, is a function. C. Now that's got a gap in it. So what that means is there's an input value of 0 that doesn't have anywhere to go because 1 over 0 is not defined. So there's a gap there. There's an input that doesn't have a unique output. So it's 1 to 1, I'm guessing, but it's not really 1 to 1 because there's a gap there. There's this input that doesn't have anywhere to go. Other than that, it's 1 to 1. So we could say that except for x equals 0, the function is 1 to 1. Each input has 1 output. Now as it stands, it's not a function. If we were to exclude 0, it would be a function. So as it stands, it's not a function. if we were to say, right, okay, y equals 1 over x, and then we state that x is not equal to 0, it can't be equal to 0. If we add that bit of information, that turns it into a function. That gets rid of the problem with this input of 0 having nowhere to go, because we're saying, right, we're not including 0. And the last one, D, now that is many to one, because you can see that two different inputs go to the same output. That's allowed because each input has one output. That's not a problem. So this is many to one, many to one, and if it's many to one, that is a function, So we need to work out the range of each of these functions. That basically means working out the outputs. What outputs do we get given the inputs that we've been given? Now sometimes that can be a whole set of numbers. It may be just a few numbers. It may be actually like a set of like 1, 2, 3, 4. Could be our output numbers. So let's write down and work out what those output numbers are. So in the first one, our domain, the numbers that we're putting in are 1, 2, 3, and 4. So let's put those numbers in and work out what output numbers you get. So 3 times 1 minus 2, 3 times 2 minus 2, 3 times 3 minus 2, 3 times 4 minus 2. So I get 1, 4, 7, and 9. So that's my output numbers. So I would write down range, and I can write my range like this in curly brackets, and remember we write y because they're the numbers that come out, and the numbers that come out 1, 4, 7, 9. So the way that you write the range, very similar to how you write the domain, but we just write the word range instead of domain, and we write y or f of x. So you could put f of x here instead of x. So you could put f of x there instead. We might do that in the next one, b. Right, so we've got x squared, and the domain goes from -5 to 5. A graph might help. So here it's not just single numbers, it's a whole set of numbers. So here's my graph of x squared. My input numbers are going from -5 to 5. And I can see the range. Range is from 0 to whatever number it reaches to up there. So I look along the y-axis to find my range, and this is where sketches help. Now, because it's the graph of y equals x squared, it's going up to 25. So my range, and we'll use f of x this time, or g of x, is going from, well, you can say this, that it's all real numbers, but those numbers go from 0, greater than or equal to 0, up to 25. And the last one, C. So again, a graph is going to help. And it's 1 over x, our function, which is like that. And we're going from 0 to 3. So our inputs are from 0 to 3. And we want to work out what the output numbers are. So we need to, it's greater than 0. So we basically need to work out from here. So actually the range, well, the bottom part of the range, that's the lowest value down here, and it actually goes up forever, doesn't it? Like that. So I'd write the range and this is h of x, all real numbers, but those real numbers, well, the lowest value down here is going to be 1 over 3 1/3, so it's greater than or equal to 1/3, because you've got greater than or equal to 3. So h of x, or we could say that h of x is greater than or equal to 1/3, which means I've just spotted from this last one, I shouldn't really write x here, that should be g of x. And we also need to state if the functions are one-to-one or many-to-one. So now we're just dealing with functions. So the first one here, this is 1-to-1. So all linear functions are 1-to-1. Quadratics, where here we've got two inputs going to one output, so this is many-to-one. Quadratics tend to be many-to-one as well, depending on the range. And the reciprocal is in that range is 1-to-1. So, or sorry, in that domain. So because we've restricted the domain, we've excluded 0, it now becomes 1-to-1. This is a function which basically has one rule, this, up to 1, and then from 1 onwards it's a different rule. And where they both happen is at 1. So basically we're going to have one graph that goes from -infinity up to 1, and we're going to put an open circle where that graph ends, and then this graph, the x squared plus 3, takes over. So the first thing we're going to do is to work out what's this, what I call like critical value at 1. Where is each graph going to start and finish? Well, if I put 1 into this function, I get a value of 3. So that's where this one ends. Where does this one start? So that's going to be 1 squared plus 3. So this one starts at 4. So let's sketch what that looks like. So this is part A. Like this. So the first one, the 5 minus 2x, if you think of it as minus 2x plus 5. So this is a linear straight line graph that's crossing the axis at 5. It's sloping downwards, and it's going to slope downwards until it gets to a value of 3. So it's going to look like this. So this is only a sketch, so this is not to scale. So a straight line going down like that, and when it gets to here, I'm going to draw an open circle because it doesn't include 3. So here I've got the graph of f of x equals 5 minus 2x. Then the other graph is going to take over, the quadratic. Now that starts at 4, so it's going to start from here. Now this quadratic is U-shaped, and because it's x squared plus 3, it's going to be U-shaped, and it's going to go like that. Yeah, so but I basically want to carry on the graph from sort of round about there. Yeah, now this is the number 1 here, so it needs to carry on from 1, and it's going to look, I'm guessing, so I'm going to have a closed circle there. I'll just trace out my quadratic again. So that bit, that's what I want to draw. Like that. And that is the f of x equals x squared plus 3. Okay, so that's what our sketch is going to look like. It's continuous, even though there's a gap in it. As you go across on your x up to 1, well, 1 actually is part of the x squared plus 3. There's no gap this way. Yeah, there is a gap this way. So there's a gap here, but actually it's not a gap in a range, because actually that covers, this one covers that gap. So that's part A. Part B, we want to solve f of x equals 19. Now at 19, so this is not to scale at all, 19 here, you see 19, that will actually go across, f of x can be 19 for either graph. So we need to actually solve not only 5 minus 2x equals 19, but also x squared plus 3 equals 19, because of where the 19 goes across, goes to both. Yeah. Now that may not be the same for all values. So for example, if I had to solve f of x equal 3.5, well, I would only put it into here, because that's 3.5 only goes to that graph. It doesn't touch this one. So it all depends on what f of x equals. In this case, it's both graphs. So negative 2x, if I take away 5 from both sides, 2x equals 14. So x equals negative 7. So that's basically negative 7 here. And then if I solve this one, x squared equals 16. Now we know that x would be plus or minus 4. But if we look at the graph, yeah, that can be plus 4. But minus 4 over here, that's not part of the x squared plus 3. So we actually ignore the negative solution and we just go for x equals 4. So those would be the solutions. So this is really important to have the sketch and refer to the sketch to help you solve the correct equation, and maybe to reject any solutions that don't exist in this graph. Right, you should now be able to do exercise 2b on pages 30 to 32 of the textbook.